So let's start with solid. Let's look into the thermal expansion in solid. So to understand this, we have to dive deeper. We have to dive to atomic level, right? We're zooming into atomic level. So there are two ways to explain this. First step would be to use ball and spring model, and the actual one is asymmetrical Morse. Okay, so this is the other theorem, which actually this is the one which we need to actually understand, but this is a stepping stone. So we'll start off with this. In this video, we're looking at the ball and the spring model. So here we have. So in the ball and the spring model, the atoms are considered as hard balls and the interatomic bonds are tiny springs. So basically what we're looking at is, so we are looking at, say, a ball and one more ball, and they are attached by a spring. So you can imagine a three-dimensional structure like this, So this is going on along the y-axis. You can imagine that. Sorry, yeah, this can be y-axis. So if I consider this as x, this as y, and this as z. So it's in all the direction, guys. It's in all the direction. Okay. So in this manner, we have atoms being connected and we are looking at them moving around. So they are pulling and pushing and they are pulling and pushing. So all of them are moving. So I'm just considering one of it. I'm considering this to be at rest, for example. And say this is moving with respect to, so this particular atom or molecule with respect to this, how does it move? So that simulation is what I'm trying to show over here. So if it goes too far, sorry, it goes near. So left is near. So the other atom is here actually. I think I do have the other atom as well. Yeah. So the other atom is over here. Think that it's stationary. From its perspective, it's stationary. So the red atom or the molecule, it goes left and right. When it goes left, this atom pushes it away. When it's going away, it pulls it back. So this particular arrow indicates the direction of the pull and the push. So this is what is happening basically. So this explains the vibration. Okay, right? You got it? Now, so that is your simple ball and spring model. The spring behaves symmetrically. They push back when the atom comes near, right? Too close, that is repulsion. They pull when the atoms are pulled apart. So you can imagine if you take a spring, and if you have not done that, you should do that. You take a spring and you pull it. What happens? It goes back and forth. It does it very fast. So, and it comes to rest too early for us to notice that. But if you take that fraction of a second and observe it carefully, you can see it going back and forth. So that's what it means. So let me pause this actually. Then atom continuously vibrates about a equilibrium separation. So there's a point around which the atom goes back and forth. So here, for example, if this is equilibrium, it goes to the right and to the left. So this particular displacement with respect to this point, the mean position. Okay. So if that is the mean position as well, the right and the left displacement will be equal. So that's why it's called the mean position. So in our case, for this particular atom or molecule, the mean position is, can you see where it is? Take a guess. Where is it? It's the point wherein the arrow switches, that is 3. So coming on to this diagram, you can see that at 3 something is happening. This is energy and separation graph, and this is this is just normal representation. So these are coordinates, simple coordinates. So point is, it is moving around the mean position. That's what I'm trying to tell over here. Now we'll come to energy, the other graph. Energy of the oscillation. For a pair of atoms, the total energy is equal to K plus U, where K is your kinetic energy and U is your potential energy stored in the spring. Right? So we have seen this in spring system. Okay. So when we have a frictionless surface, I hope you guys remember this. Of course, this is a hypothetical situation. So if you have a wall and a very smooth surface, so basically friction is 0. Friction between this and an object. And if this is connected to a spring, so what happens if if this is the mean position, if I happen to pull it, so what happens? So the bob, let me show this. So the bob goes forward, slows down. It has the highest speed over here, goes to the left, highest potential, and goes to the right with the highest speed, and goes to the right extreme, the highest potential, and the kinetic energy is 0 over here. So I hope you guys remember the graph as well. So this keeps happening. Right? So that keeps happening. The same thing is seen over here as well. Okay. So now just a second, let me go back. The total energy is sum of kinetic energy plus potential energy. Right? So the potential energy versus interatomic separation graph. Actually, I have here energy plus atomic separation. So let me go to that. How to read the graph. So now we are trying to understand this graph. Okay. So the heading is actually, I should change the heading. Energy versus, so ignore this potentials. Guys, 1 minute. Let me do that. Okay. I'll warn you guys over here. This is the confusing part for many. So many of my students, they get confused at this point. So understand this very clearly. Okay. So let me actually go to this itself. See, this red line is the energy, total energy the system has. Okay. So if I increase the temperature, the total energy increases. If I decrease the temperature, the total energy decreases. Okay, yes. And what does this curve do? I'll be talking about that. So basically, this red line is your sum of kinetic energy plus potential energy. Okay. So that's the sum of your kinetic energy and potential energy. So let me go to this point. So how do you read this graph? The curved line represents the potential energy. The curved line represents the potential energy. Okay. So let me at exactly in the middle. I don't know how I stopped it. It's exactly in the middle. So it has the highest or the lowest potential energy. The curved line, forget about everything else. Just look at the curved line. Is it the highest point or the lowest point of the potential energy? Yes, it's the lowest point. Okay. So you understand this. When you have something on the mean position, right? What is the potential energy? Try to recall. In the mean position, the potential energy is 0, while the kinetic energy is maximum possible value for that particular situation. Okay, so that's what is happening over here. And the blue line, let me go to the graph. The horizontal line, the total energy, the horizontal line is the red line. Total energy of the vibrating atoms. Vertical gap, so this gap that is between the horizontal, that red line, and the bottom of the curve shows us the kinetic energy. Okay, so this gap shows us the kinetic energy. This blue line shows the potential energy, and this red line shows the total energy of the system. Is that clear? Potential, kinetic, and total energy. Point where the horizontal line cuts the curve, turns point maximum and minimum separation during the vibration. Okay, so this is, basically this, sorry guys. This red line, wherever it's meeting the curved line, right? The potential energy and the total energy, wherever it meets, that's the extreme point. That's the extreme point it reaches, the atom reaches. This is an important graph to understand. This will be used in the next not the same graph, but the concept will be used in the next graph also. That will help you understand why on heating a material expands. Okay, so again, let's have a look. Now you have a graph. And you have, let me use blue itself. You have this. Not exactly that, but this is symmetrical, supposed to be. Okay, this looks okay. Say this is the maximum point, and that's your minimum point. So if I have to map it, so if this is O, if this is A, and this would be B, this is nothing but your A, O, B. That is a position. So along this axis, you are looking at the position. Along this axis, you are looking at, in this case, it is potential energy. So this is your maximum potential energy when you have the particle to be on the left extreme. So at point A, this is 0, the energy is 0. Sorry, I'm writing it ulta. So this is A and this is max. And this is the mean position. That's a 0. Sorry, mean position is O actually. So actually let me change it to P. It's kind of confusing. So P, so this is P comma 0. The potential is 0 over here. And this is B comma P max. Okay, so let's have some, let's use some common sense and talk about kinetic energy. Where will the kinetic energy be maximum? Obviously, when the potential energy is minimum, that's where the kinetic energy will be maximum. So if you guys remember, we also did kinetic energy graph in the same thing. So the kinetic energy will be maximum at P. All the energy in potential energy gets converted to kinetic energy, and it becomes 0 at the extremes. So your graph will look like this, right? So basically, if I add this to, if you guys remember the chapter, the spring chapter, right? Spring constant and all of that. So if I add this to, it will add up to a particular value, and this is constant. The sum of those two is constant. Now what we are doing is, we are not talking about this blue line. Let me not actually change this. Let me keep it for you guys. Actually, a few more corrections. So we are not talking about this kinetic energy over here. We are asking, the graph is asking us to find the kinetic energy by subtracting the potential energy from the constant value. Okay. So let me change this so that. So kinetic energy is represented with dotted blue line. And the potential energy is represented with solid, whatever that line is. It's somewhere purple and blue, and yeah, you guys can name it. Sorry, I'm not that great with this color naming. It's somewhere in purple and blue, right? Anyways, point is, instead of doing this, they're asking us to do this. That's it. So if I take the difference over here, right? If I take this difference, that is, if I take the difference of the constant, say the constant is 10. Let me actually take some values. Say this constant is 10. And by the way, this is 0 over here. Okay. So that's 0. So 10 minus 0 is 10. So the difference is 10 over here. Since the difference is 10, your kinetic energy will be maximum at this point. And say this is somewhere in the middle. It looks like middle. This is 5. So here the kinetic energy and potential energy are equal. And this extreme, okay, potential energy is the highest. So 10 minus 10 is 0. The kinetic energy is 0 over there. Does it make sense? It reflects your spring experiment and understanding that we have, right? And now you can look at the animation. Can you see that? Whatever we just discussed, the same thing is happening. So I can increase the energy. Okay. So there is an issue with this. I'll explain the issue. But did you guys understand to this point? If not, please think about it. Take some values. Please think about it. You have values over here, R, K, E total, U and K, E. So I'll pause a few more times. And you guys also can simulate this, right? In our website, you'll be able to simulate all of this. So total energy is 31.4. Look at that. Is it changing? It is rock solid. It's not at all changing. What is changing? U and Ke. So U in the middle is almost 0. We are almost in the middle. It's almost 0. Kinetic energy is maximum. It's almost equal to the total energy. Can you see that? So that's all I'm trying to make you guys realize. Now the potential energy will be approaching maximum while the kinetic energy is almost 0. Oh, I couldn't make it. Let me try now. Okay, it's pretty fast. Oh yeah, I got it. Can you see that? So potential energy is maximum on the left and the right extreme. Okay, right. So that was in detail. I won't be explaining this in the next graph. So next is now effect of heating or cooling. What happens when we heat and cool? So we saw that over here. So if I increase the temperature, what is happening? The total energy of the system is rising. So if I reduce the temperature, it fell. The total energy fell, right? So you can see the vibration is slow and aram and it is very minimal. So when I heat it, the vibration is maximum. And so the expansion happens. That's the whole funda. So heating, total energy increases. The horizontal line moves up. Okay, I could have written this actually. Could have changed this. You guys can put an arrow. You can tell heating. You can put a down arrow. You can call it as cooling. Total energy decreases. Horizontal line moves down. Amplitude of the oscillation decreases, right? That makes sense. Okay. Now, but there's a limitation. What is this limitation? Because the potential well is perfectly symmetrical, right? This is the potential well. It is a well, right? It is in a well shape. The average position of the oscillation always remains exactly at R0. So it remains exactly at 3. The mean value for all of this, okay, you take up any point, any line. So any horizontal line over here, you take up any horizontal line. If I increase, decrease, whatever I do. If you take up the extreme values, take the average, it will be 3. Here too, it will be 3. Here too, it will be 3. Right? Here it's 1. Can you see that? It's 1 and this is 5. 1 plus 5 is 6. 6 by 2 is 3. Good example. And let me try increasing the energy to 30, decreasing the energy to 30. Okay, almost 30. So 30, you can see it's not in good value, but 1 point, it looks like 3 and this will be 4.7. So 1.3 plus 4.7 would be, how much guys? 5, 6 again, right? 6 by 2 is 3. So you take up any such two values, you will end up with 3. So why is it an issue? So exactly R0. Okay, let me start reading again. Because the potential well is perfectly symmetrical, the average position of the oscillation always remains exactly at R0. Large amplitude only makes the atoms swing equally to the left and the right. So what's wrong in that, right? So whatever the temperature is, it just makes the atom swing about the equilibrium position equally far away, exactly whatever exact value you move to the left. If I move, say in this case it is 1.5, say I'll take it as centimeters, it will move 1.5 centimeters to the right as well. So because of this, the mean separation between atoms does not change with temperature. That's an issue now. See, between atoms, there's a huge space, right? They're not that close as well. There's a huge amount of space. So if that is the case, why will the object expand then, right? This symmetrical spring model predicts zero thermal expansion. So according to this, object will heat up, yeah, temperature will increase and all of that. But there should not be an expansion. Remember, there is huge space. Okay. So if this is one atom, the another atom is over there. Okay, guys, I'll give you guys the statistics. Just a second. Okay, guys. So the ratio turns out to be this. I mean, you can imagine molecules and all of that. So the ratio turns out to be almost 1:4. So there is pretty decent enough space for the vibration to happen. So actually, I should be talking about in terms of vibration. The amount of vibration, right? Even if you increase the temperature, so the vibration can be happening over here. I don't know if you guys are able to make that out. I'm moving my cursor. So the vibration can happen over here, more temperature, it can happen here. So it has enough space to move around. So why does an object still expand? That is not exactly explained with this particular theorem. That's the problem. It is close, but not the exact one. That's what we're going to study in the next video. So this video, we spoke about what happens in a solid when we, give it extra energy, when we heat it up. So the model is called as ball spring model. So it takes up the concept of an ball being attached to a spring and it's on a frictionless surface. So when you pull it and leave it, it goes back and forth, and it will do so. So when this is happening, the kinetic and the potential energy keeps varying, but total energy remains the same. So that being the case, we got to see this, what happens when we increase the temperature, right? So the vibration about the mean position, it increases. But in all of the cases, the total energy remains constant. That is the potential energy plus kinetic energy adds up to that value. That we understood. But end of it, we saw an issue. The issue being this. The atoms, the molecules have enough space for them to move around. They have enough space for this particular, for particular temperature, they have enough space to move around. They need not expand. As per this, they need not expand. They can just stay over here without any hindrance to the other atoms' vibration and all of that. They can just be there and keep moving around, and he also can keep moving around. This being the case, why should an object expand, right? If all the atoms are just there and vibrating faster, what is the issue? Why should we make extra space? So that is what this theorem can't explain, and that is what we are going to look into in the next video. For now, you guys I'll show everything. It's left to you guys where you guys want to write and what you guys want to write. So for this, you guys can relate it to this, I guess. So that same graph can be used. Put an arrow over here, and this will be heating and this will be cooling. And then the issue. You should have 3 graphs at least. And if anything you guys want to write, it's over here. So this ratio is to do with the atom space and the empty space between them. The sphere of influence, basically, not sphere of influence actually, but yeah, atom space with respect to the space of a solid. That's the ratio. Okay, so let's solve the puzzle. Let's understand why exactly object expand.